Welcome to Study Loop.
In this problem, we have some kind of block here being lowered from a winch or something up here. And then we have a cable, obviously attached, that's unwinding. It's moving down at 3 feet per second initially, and then it suddenly stops. And so what we're told is that we can consider this cable to be a spring because it's elastic. It's not rigid. And the spring constant of a uniform cable or rod is the cross-sectional area of that rod times the Young's modulus of the material divided by the length of the rod. And that's really just a consequence of the stress equals E times epsilon. So if we write the stress as F over A equals E and epsilon is delta L over L, we can see that K is F over delta L, and we get this. So this thing weighs 4,000 pounds, and again it's going down at 36 inches per second. The diameter of the cable is 0.4 inches. The Young's modulus is, let's see, did it actually say what the material was? I don't see it in there. Anyway, they give us a Young's modulus, and then we know that it has been lowered 360 inches or 30 feet when it suddenly stops. So we can find the spring constant because we're given all this information, the cross-sectional area, E and L, and that is 10.1 times 10 to the third pounds per inch. At this state here, initially it has some kinetic energy. There will also be technically some potential energy in this cord because of the weight of this, but we're basically, that's already kind of being accounted for because it's already been stretched. So we're not going to kind of the difference in the potential energy going from when it just stopped to where it hits its lowest point because of the cable stretch. It's just going to be 1/2 K times the difference in the length of the cable. And so we know that now that UAB must equal TA because of conservation of energy, and we know TA and we know K, so we can solve for delta Y, and that is 1.5 inches. Now we could also say that, well, we could be worried about what length this is. Is this the length before it's stretched or after it's stretched? Well, if we're talking about small deformations, we basically just consider that it's the length before it's stretched as a good approximation. And you can see that because you can compare 1.5 inches to 360 inches. And obviously this is very small compared to this. So if we use 361.15 inches in here, we would get something that's extremely close to this value.